All right, guys, let's get started. So last time we talked about min-cost flow and the Goldberg-Tarjan algorithm. So just as a reminder, we had this issue with lemma 3 last time. So I sent out an email with the corrected thing. It's also in the notes. So come talk to me if you still have questions about it. But in the meantime, can anyone remind me about what one of the main insights was behind Goldberg-Tarjan? How do you actually choose the augmenting cycle? So that was one of the key things. Uh-oh. So how do you choose the cycles in Goldberg-Tarjan?
Be careful. Most negative?
Most negative mean.
Most mean.
Most negative mean. Because actually for Goldberg-Tarjan and for min-cost flow in general, the big issue is that if we chose the most negative cycle, that would be something that would work well, but that optimization problem is hard, is NP hard. So the main insight behind Goldberg-Tarjan was that we actually wanted to augment along a cycle of minimum mean cost. So this is where we talked about the analogy between things like Ford-Fulkerson and Klein's cycle canceling algorithm. Both of them are things that work in pseudo-polynomial time. When you talk about getting something that actually works quickly and makes as much progress as possible, there was a way to fix Ford-Fulkerson just to look for the fattest paths. But when you try and do the same thing in the context of min-cost flow and look for the most negative cycle, you get stuck that you can't even compute what that is. But instead, if you look for the cycle of minimum mean cost, that is something that you can do. And last time we analyzed how well it worked and got a weakly polynomial time algorithm. So today, what we're going to be talking about is we're going to start talking about linear programs. So we're going to spend some time on linear programs. And the first 2 lectures on it, we're just going to develop some of the basic theory behind LPs. But really what we're going to do after that is we're going to use it for a lot of interesting reasons. We're going to give approximation algorithms behind it. And we're even going to go back and revisit some of our favorite flow problems and interpret them through this language. Now, linear programs actually were, one of the founders of them was Danzig. So has anyone heard of Danzig? Can anyone tell me, there's a famous story about Danzig. Does anyone know it? Yeah?
There were 2 problems on the board, and he came into class late, and he thought they were homework problems, but then it ended up that they were open problems and statistics, and then he ended up...
Exactly. So actually there were 4 questions. You only saw 2 of them. So he didn't do that well on that homework assignment. So it's a lot of times described as like the power of positive thinking, that if you think something actually can be solved, then maybe you can. So that's one interpretation for you guys. I'm going to give you a different interpretation of it, which is if I want some questions solved, even if they're open, I might as well as assign them as homework. So to that end, let me give you a mandatory homework assignment. You guys all have to turn this in before the end of the semester. It's going to be very harsh on the grading on this. And if anyone comes in late, so if you see your neighbor coming in late, poke them and remind them about this homework assignment. Let's see what they say. So here's your mandatory homework assignment. Let's make it due April 1st. So I'll give you the following question, which has a very short answer. So let F be a family of sets which is closed under union. So we have that if A and B are in this family F, that the union of those 2 sets is also this family F. Now what I want you to prove is that there is an element, X, which has the property that it's in at least half. So if you look at all of the sets in the family where X is in A, this better be at least half of the sets. Okay? So mandatory homework assignments. All right. So anyone actually ever...
Finite number of elements?
What?
Is the universe in a sense live in finite or?
Let's say it lives in a finite set of elements. After all, it's a finite family of sets anyways. So just prove that there's an element that's in at least half of them. Due April 1st. So we'll move on to linear programs. Anyone actually know what this is called? No? It's actually a notorious open question in combinatorics, so you're welcome to think about it. It's called the Frankel union closed set conjecture. It's one of the examples of something that's very easy to state, but actually, as far as you can tell, very, very difficult, if even true to begin with. In any case, so let me move on. So this is my homage to dancing. And what we're going to do today is we're going to talk about some of the basics of LP theory. But let me first give you a little bit of the context, to place this in context of some of the things that we already talked about. So what I claim is we've already, in this class, seen many examples of the following pattern. We have some optimization problem. And the way that we actually understand this optimization problem is through developing certificates of optimality. That's the way we think about how we can make progress on the optimization problem, and when we know that we're actually done making progress. So we have one. So someone give me the first simple example of this paradigm where we have an optimization problem and then we have some certificate of optimality. What's the easiest one we've done?
You want to get max flow and you show max flow.
Exactly. So we want to show max flow. That's one instance of this sort of parallel. And the way that we do this is through min cut. Now the only other example that we've talked about are things like min cost flow. And the same way that we also had some certificate of optimality that told us that we were done making progress on min-cost flow. Yep.
No negative weight cycles?
Yes, exactly. So just to expand on that, we really had, once we already knew that it was a max flow, the thing that told us that among max flows that actually had the minimum cost was that we had a potential which had non-negative reduced costs. So that was even, in fact, a way to simply prove that there is no negative cost cycle, was even to find the corrections for what potential, how to create the reduced costs, which all of the edges have non-negative reduced costs, and hence you can't create a cycle whose average is actually negative. So this is a very common paradigm in algorithm design, is that you take some optimization problem, and the way that your algorithm works is by identifying some type of certificate of optimality that tells you how you can make progress and when you can't make progress when you're done. But actually, these are all examples. There are many more examples that we're going to cover. So there are many more examples more broadly in combinatorial optimization. Can anyone think of another example of something in combinatorial optimization that fits into, or anything else actually that fits into this type of paradigm? Yep.
A lot of the problems in NP.
A lot of problems in NP.
All of them.
All right.
This is a different notion of certificate of optimality.
Yeah, this is a different notion of certificate of optimality. That's true, definitely. I guess here I mean,
It doesn't
we're
support
really...
that it's actually optimal, right? If you see a traveling salesman solution, you know that traveling salesman solution, the true one must be at least that good.
Yeah.
But you have no way of directly knowing that there's nothing better.
Yeah, exactly. So what I'm actually talking about here is that these types of things give us ways to prove that the problem is in the intersection of NP intersect co-NP. So one other example of this that we'll touch on later are things like zero-sum games, where we talk about things like the game value, that we can talk about how one player would play the game to ensure him that he gets at least this value, and how the other player can prove that he can't actually do better than that by creating a different strategy. But the main point is that these examples are actually derived from the same principles, which that most of these examples are actually derived from the general theory of linear programming. So we're going to develop some of the theory of linear programming today, and we're going to revisit some of these examples to build up some intuition about how all of these fit into a nice geometric framework, and that'll give us a language for talking about lots of other problems. See, the point I'm trying to make is that a lot of times when you're faced with an optimization problem, just knowing that it can be cast as a linear program already gives you a terrific amount of mileage, because you can tell what the general theory of LPs tell you. That tells you a lot of the structure about your problem that you can actually exploit to give algorithms. So we're going to be studying this more general family of problems called linear programs. So let me define what linear programs are. So I'll give you the definition of linear programs in what's called canonical form. So there are a few different ways to talk about what an LP is. They're all equivalent. This is one form that's actually called canonical form, which we're given some optimization problem where the goal is to maximize some linear function. So x here are our variables, and this is our linear function that we'd like to optimize. And we have some constraints on which type of x we can choose. We have some matrix inequalities, so A is a matrix. And we have some constraints that however we set these variables, A times x is less than or equal to some vector B. And we also have some constraints that x is non-negative. So here, this less than or equal to sign is interpreted as a component-wise constraint. So B is some length m vector, A is some m by n matrix, and when we multiply that by the vector of variables, we get out a length m vector on the left-hand side, and the constraints are that it be entry-wise less than or equal to b. The same way we have the constraints that x be component-wise non-negative. So this is called the primal in the canonical form, and there's a related optimization problem which is going to play a key role in what we talk about, is what's called the dual. So you can think about duality right now as just a formulaic way of going from this type of optimization problem with linear constraints to a different optimization problem with other linear constraints. And we're going to develop the theory about how these two things are related and see what that tells us about some of the problems that we've already studied. So the dual for this is, all you do is you create a new linear optimization problem where the goal is to optimize some linear function. Now y is your set of variables, and you want to optimize y so that when you left multiply by a, it's component-wise at least this corresponding vector c that comes from here, and that y itself is entry-wise non-negative. So this is what's called the primal and the dual for canonical in the canonical form for LPs. And we're going to develop some of this theory today. So is this, do these types of optimization problems make sense? Are there any questions about this? Yep.
Isn't the dual one y is also the variables?
Yes, exactly.
And c is just constant?
Yes, but it's the same c that came from here. So what's going on is that you're actually, so if you think about it as if A is an m by n matrix, then x is a length n vector. Now the important thing is that then y itself is a length m vector in order to actually make the dimensions match up. So what's going on is that you take the constraints and you put them in the objective function. And when you take the constraints here, you put those, when you take the objective function here, you put them down into the constraints of the other. So you should check that the dimensions work out, but this is just a formula, a recipe, for going from some definition of a primal to what's called the dual. Why this makes sense shouldn't yet be clear, but at least these optimization problems themselves should
But
make
if
some
you put the
sense.
constraints into y, then that means that you're solving for the constraints that would make the problem work.
You mean you're asking what's the intuition
Yeah.
behind the dual? So we'll get to that.
Oh.
We'll get to that slowly. So actually the game plan for today is we're going to develop things like weak duality, understanding what the relationship is between these optimization problems, map them back onto things like max flow. What we'll do next time is we'll prove what's called strong duality, and I'll actually give you an interpretation of what's going on with the primal and the dual through physics and through complementary slackness. So we'll see different layers that how to actually parse this definition. Are there any other questions about this?
Why
Yeah?
are we not folding x greater than or equal to 0 into the ax less than or equal to b?
Because it's called canonical form, and this is, the definition of canonical form. So the point is that what you're asking is that there could be many other ways that, we could have folded x greater than or equal to 0 into the constraint A. Then we would get a different form for the primal. That'd be something else, and that would give rise to a different form for the dual. That's all perfectly valid. There are different primal dual pairs. This is one of them. And you can derive all the others from actually doing the types of elementary operations we're talking about, and we'll do those later in class. Any other questions about the primal dual pairs? You shouldn't yet understand what they mean, but let's develop it. So, the first thing that I want to do to unravel some of the mystery about what these two things are is I want to prove the most elementary thing in LPs, which is called weak duality. And actually, I guess let me add one piece of nomenclature down here. Well, we say that X is feasible, so that's an important keyword in LPs. We'll say that X is feasible if it meets the constraints in P. And similarly for Y. So a priori, when I give you some instance of this linear program, there might be no X that meets those conditions. Maybe all these constraints are contradictory. In that case, the linear program is infeasible. Something very different happens there. But the starting point for a lot of the statements about LPs will be assuming that we have some feasible solutions for P and for D, and we want to show some relations between them. So we have a similar notion for Y as well. Y is feasible if it meets the constraints in D, forgetting about the objective function. Now the important thing for weak duality here is that it tells us that if X and Y are feasible, then there's actually a relationship between how good they are. If we take X and plug it into the LPP, then we get this objective value. The claim is that this is actually upper bounded by the objective value that we get for the other LP. So what this tells us is that the primal and dual are useful for proving bounds on each other. When we have this type of inequality, one way to show that we can't make any more progress and there's not a better X hiding somewhere out there that is still feasible but increases our objective function is just to use some other Y to try and certify it and show that there really is a ceiling on how high it can go. So this is called weak duality. Let's prove this. It's a very short proof. But then we're going to map it back onto things that we already know and see how it's telling us just a more general version of things that we've already proven so far. So are there any questions about the statement of weak duality? Makes sense? Yeah? All right, so let's prove it. Short and sweet proof. So what I claim is we're just going to do the following. Well, we know that X is feasible, so it's non-negative. That is one of the constraints in the primal LP. And moreover, we know that Y satisfies another family of constraints because Y is feasible in the dual program. Now this pair of constraints is enough that since X is non-negative, we can actually right multiply this vector constraint and get another valid vector constraint. See, if X were not non-negative, then we couldn't say this in general, right? So if X were component-wise, entry-wise non-positive, then by right multiplying it, we'd actually flip the inequality. And even worse, if X had some positives and some negatives, well, we couldn't make any claim about what happens when we right multiply by X, right? But it's really the pair of these two constraints that allows us to take this and actually derive something new, which is just that if we right multiply by X, then we get this constraint, right? So now what I want to do, this is the mechanism by which I'm going to prove weak duality, is I have this quantity on the left, which I now know as an upper bound for my objective function, C transpose X. Now, how should I go about proving the other part of weak duality is also by using this quantity, but now showing that it's upper bounded by Y transpose times B. So how should I go about doing that? What pieces of the inequalities, using the fact that X and Y are feasible, should I use to derive that type of constraint? Yep.
In the primal, you have the requirement that B is greater than or equal to A X.
Yes, good.
So you can substitute that in.
And y is not negative.
And Y is non-negative. See, in fact, there's another way to think about this, which is, I better use up all of the constraints in this, otherwise something is going wrong. And I've used up the X as non-negative and this constraint right here, so the two corresponding constraints that pair up with each other are the things that I need to use in order to get the other side. So now, all we can do is, using the other two constraints, ax less than or equal to b, and y is greater than or equal to 0, well, all I can do is I can left multiply by y transpose, and then that gives me the other side, because I have y transpose ax is itself less than or equal to y transpose b, and then combining these two inequalities, I get exactly the thing that I wanted, right? So this is a very simple but very powerful statement that this gives us a way to actually upper bound and show that the primal can't make any more progress. So using our mapping, for max flow versus min cut, let's try and think about what weak duality implies for max flow versus min cut, something that we already know, but let's see it in this language. So that's our plan right now. I'm going to do it in a little bit of a strange kind of way, is that, a lot of times when you think about linear programs, you think about A as itself being not too large a matrix, right? Because you're thinking about this as being an optimization problem that you'd actually like good algorithms to solve. Things which run in polynomial in the description length of this problem. But actually there's a lot of value to applying LPs even to very large matrices. So let me actually work with a very large matrix and show you how we can use weak duality to actually think about max flow versus min cut in this general language. So this is another way of thinking about how to use it. So let's apply this to max flow. And I'm going to do this pretty bizarre thing that I'm going to let PST be all the ST paths in some directed graph G. Okay? So that's a huge set of paths, right? That's potentially exponentially many paths. And I'm going to create an exponentially large matrix. Just because. So one way to try and write out the max flow problem now, using this language, is we can create a variable for each of the different paths in the set of ST paths. Now we want to maximize the total flow being sent by these variables, but we have some constraints on how much flow we can actually send on the different paths. So one way to try and do this is we can look at all of the different paths in the set ST, and let's say we only look at paths that contain some edge E. This is a directed edge. Well, one constraint is that we need that the total flow going along those paths is at most the capacity of that edge to begin with. Otherwise, we're just using up too much flow on these paths that traverse this one bottleneck edge E, right? So this is a valid constraint. And we also have that all of these XP variables are themselves entry-wise non-negative. So what I claim is that this optimization problem really is can be expressed as in this form, as just some vector x, which each of these entries are themselves the amount of flow being sent on a different path. Now, what would the A matrix be if we want to map this type of optimization problem into this formalization? It would be an exponentially large matrix. Any hints about, any ideas about what it should be? Yep.
Each row should have all the edges, sorry, all the paths crossing one edge.
Yes.
Because those don't belong that up.
Exactly. So let me create this gigantic matrix A, which we can think about as the columns are indexed by paths that go from S to T. And we can think about the rows then as being different edges, arcs in our graph. And then the entry in this matrix is 1 if and only if this edge is in this path. So when we take this matrix, which is gigantic, right, because it has tons and tons of columns, one for every possible path on the graph, when we multiply it by this vector x of all of the different flows along the path, then we multiply it by A, what we're going to get out is we're going to get out a vector, which the entries of which represent how much flow traverses each edge. And we have the constraint that those flows need to be at most the capacity. So this is exactly what we get when we try and cast this LP. Now you could write max flow using not exponentially many variables and constraints, not one variable per path. But actually one of the amazing things is sometimes you understand the theory a little bit better by expanding it in a more naive way. So you can get mileage out of expanding it either in a concise or really redundant way with one variable for each of these paths. Yep.
Is there any reason why the conservation constraints are not part of this?
So exactly. So that's a great question. So why aren't conservation constraints a part of this? Because we've actually already decomposed it based on paths. So every time we actually augment along a path, if you think about a single path in it, then the flow going on all of those edges in the path automatically implies conservation at everything but the source and the sink. So that's exactly the point, is that I could write this as a smaller LP, where instead I incorporate the capacity constraints and the conservation constraints too. But when I've expanded it out this way, based on the different paths, then I've actually avoided the conservation constraints. Yep.
So to be clear, this can't encode all possible flows. It can only encode the flows that can be path decomposed, like not the ones that have to include cycles.
Yes. Yeah.
We could add cycles to this.
We could add cycles.
It would make
but,
almost no difference.
Yeah.
What we're trying to do.
Exactly. Exactly. But this at least is a good example of trying to get your head around how to actually map something that's not completely, obvious into this language and seeing what it tells you. So bear with me. Let's get some mileage out of this now. Are there any other questions though about how we can write this LP and turn it into this gigantic constraint matrix A? All right, let's get some mileage out of it then. So I claim once we know what A is, now we can think about what the dual is. See, once we have A, that's our constraint matrix, then the way that we go from the primal to the dual is actually just by left multiplying by a vector of variables. So the same way that this vector of variables had one variable for every flow path, every possible path between S and T, this guy right here, this vector of variables, has one variable per what? Per edge, right? So in fact, we can think about this vector of variables and what this dual means. So let me write out what this is. So I claim what we get from the dual is we actually get the following. So remember that the B vector down here is this vector of capacities. So when we take these Y variables, inner product with B's, we're getting a weighted sum of the capacities. So we're getting the sum over all edges of the capacity of the edge, that's the entry in the B vector, times some new variable, YE, that describes the variables of our dual. Now, what do the constraints look like? Well, when we take a vector of variables and we left multiply it, what we're really doing is we're adding up the Y variables along a particular ST path. So what we have is that we get out, for some path P, the sum of all of these y, e variables. And how large do we need that to be? We need it to be at least 1 for all of the different paths that go from S to t. And we also have these constraints that these y, e variables be non-negative. So does that make sense? How we got from the primal to the dual? So now we can actually interpret what this dual is. So what I claim is that actually something like an ST cut, the same way that weak duality gives us a way to take a feasible solution to the dual to prove an upper bound for the primal, so too we can think about an ST cut as being something which is a feasible solution to this problem. So that's the main question right here. This is just to get you used to thinking about LPs. So here's my question, and I'll let you think about it for a second. So how is an ST cut a feasible solution to the dual? So the same way that we proved an upper bound on max flow by actually just finding any ST cut, and then we have the capacity of that cut, gives us an upper bound. What I claim is that actually you can, just to give you some intuition about working with the primal and the dual, what I claim is you can do the same thing. You can take any ST cut, and you can actually figure out what the corresponding feasible solution should be for the dual, which is then going to prove us an upper bound. So if I take something like an ST cut, does anyone have any ideas how to go about mapping it into a dual solution? Yep.
There should be a unique path from S to T that goes through each of the edges in the cut. And you take that and set zeros to everything except for that edge itself that is in the mid-cut.
Say that again?
You set 1
Uh-huh.
for Y of the edge that is in the min-cut.
Uh-huh.
And set 0 to everything else.
Yes, exactly. Right? So here's the idea. So it's not necessarily min-cut, but that's fine. So any cut, any ST cut, we can set the variables of the dual in the following way. What we're going to do is we're going to put 1 if the edge crosses the cut. So I'm going to let E then be this arc from U to V, so it's a directed arc. And what we're going to do is we're going to put 1 if U is in the first part and V is in the other part of the cut. So if the directed arc actually crosses the cut in the forwards direction and 0 otherwise. So what I claim is that this actually is a feasible solution of the dual. So let's see why that is. So what I claim is the following. That this really is a feasible solution. So if we take any path P and we add up the YE variables on the path, where this is an ST path, I claim that this actually is at least 1. Why? Because what we've done is we've taken an ST cut where S contains the source and V minus S contains the sink. And every time we have a path going from S to T, at some point it needs to cross the cut at least once, which means that it picks up a distance, YE, that's 1. So it picks up at least one such YE. And that implies that the YE that we get from actually taking an ST cut and constructing the solution really is feasible. Yep.
Is there some intuition for why the y's are binary variables in the optimization problem? Without knowing this had anything to do with max flow and min cut, could you see immediately that, oh, these y's must be binary?
As in, so that's a great question, which I'm going to table for the next 5 minutes until I get to it. But let me call some special attention to that, because that really is something you have to emphasize here. Are there any questions other than that? Right? So this tells us that actually the y variables that we get are actually feasible. And now the remaining thing is to actually figure out what the objective function is. So what I claim is that if we take the objective value, so sum of ye times u of e, then what should this be equal to? So someone help me out here?
The capacity of the
Yes, exactly. It's the capacity of the ST cut. Because we pick up all of the edges, we multiply them by a 1 for the ye, if and only if they actually cross in the forwards direction. So adding up all the capacities of the edges crossing gives us exactly the capacity of the ST cut. So this actually tells us, in a very elaborate way, something that we already knew, right? So what does this now tell us? It tells us that anytime we have an ST cut, that we actually can construct a feasible solution of the dual, which then by weak duality implies that it gives us an upper bound on the primal. So that's just redoing max flow is bounded by min cut in a more general language. But actually it turns out that you can a lot of times do this, that for each one, in this, when you have an optimization problem in some type of certificate of optimality, what's actually going on with those certificates of optimality is that they're using weak duality underneath. So all of those examples actually may seem sort of different, even though conceptually they sound similar. Well, they literally are similar because they're all exploiting weak duality. So now I want to call out one other point that was brought up, which is really important, which is that when we actually talked about min cut versus max flow, we didn't consider arbitrary solutions to this LP. We actually considered only solutions which put 0 or 1 values. We only considered the set of cuts. But in general, this LP could assign other fractional values for the YEs that instead could also prove an upper bound just using weak duality. So there's this question, why don't those things produce an even better certificate? In min cut versus max flow, we never needed to go to things like fractional cuts in order to actually prove the tight upper bound. So that's something that we're going to see a little bit more of later, but the answer is that it turns out you could take any feasible solution of this and you could actually round it into a 0-1 solution without destroying its cost while keeping it the same. But that's kind of an accident depending on the optimization problem, that it's not always true that you can add things like constraints that these guys be binary for free. That's really not true when we talk about fancier things, like eventually we're going to talk about things like multi-commodity flow once we build up enough LP theory. And the fact that you can't do that is what's going to underlie the fact that we need approximation algorithms. So I'll leave that for now as just a little bit of a mysterious statement, but here's the basic idea. We talked about primals and duals in canonical form. We talked about this very simple lemma called weak duality. And then we saw how weak duality actually mapped onto things we've already seen, that things like the ST cut bounding the max flow, well, actually one meta way to think about why that is it's because an ST cut is a feasible solution of the dual and because weak duality holds. So what I want to do is I want to build up some more of the geometric intuition. First, are there any other questions about this? You guys seem quiet today. Maybe I'll take a pause if you guys, any questions drum up. There's this trick they taught us when I first got here, which is, if you're teaching and you want people to ask questions, what you do is you look at your watch for 30 seconds, and then everyone will feel as awkward as you are, and someone will ask a question. You ready? Yeah, that was
Why
fast.
is it called weak duality?
Why is it called weak duality? Okay, that's a great question. It's because we're going to prove strong duality later, which tells us that, I'll state it formally later, but not only can the dual be used to prove an upper bound for the primal, but in a broad sense, you can always find a solution to the dual, which actually does certify the optimal value for the primal. You need some constraints that they both be feasible, but we're working up towards that.
What's the difference between the primal and the dual in terms of the linear program?
Can you clarify what you mean by that? What do you mean by that
I
exactly?
mean, like, so you solve one, you get optimal parameters for x, right? So why do you need the dual?
You need the dual to actually certify that you are optimal. So in a lot of cases, right? So you can think about it as P and D, actually we're going to prove that they're really the same problem underneath. They're just looking at different spaces. That's actually a very powerful way of looking at things which can be cast as LPs, that once you can cast them as a linear program, then you automatically have all of the tools of duality available to think about how to build up steps in your algorithm. So the same way that for things like min cost flow, when you give me a flow, you have the question of how can you actually improve it. Well, a lot of the ways of thinking about what you can do to improve your original solution can actually go through the dual and figure out how the dual can read off a way to improve it.
And that was the min cut. Right?
Exactly.
And you checked if you could actually do any better.
Exactly, exactly.
Perfect. Thanks.
Yep. Any other questions? Don't make me look at my watch again. I'll do it. No, I think we've got enough questions. All right, so let's build up a little bit more intuition here. So what else should we do but draw a picture? Because what's going on underneath this, the main point of going to LPs is to understand how the things we've been doing are actually at their core of their geometry. So let's think about our set of feasible solutions to the primal. So let's look at all of the x's which satisfy these different constraints. So we're ignoring what the actual objective function is. But if we take a look at this set, then what we can do is I can take the first row of this constraint. If I think about the matrix A, and I can just take the first row, which is itself a vector, and then the first part of this constraint is just that vector times x is at most the first entry in B. That's a linear constraint, so it's a half space. And actually the entire feasible region is just built up as the intersection of different half spaces, right? So geometrically, what's going on? I'm only going to draw this in 2 dimensions for obvious reasons. But what's going on is that if we take, for example, the first row here, we have some constraint that should be on this side of some half space. Every x that meets those conditions have to be on this part of this board. We might have constraints for all of the different rows in there. And together we take their intersection and we get this region, which is exactly P, right? So this is geometrically what's going on. Now, the important things about this, so this is called a polyhedron. It's just a finite intersection of half spaces, of these linear threshold constraints. Now, there's a related notion called a polytope, which you could also instead describe the set as a convex hull of these different vertices along it. So we'll develop a bit more of that theory next time, but for the time being, just think of this as a polyhedron. Now, what's important about a polyhedron is just the statement that I alluded to, is it's convex. So it's convex, meaning that for any x and y in the polyhedron and any lambda in the interval 0 to 1, we have that lambda x plus 1 minus lambda y is also in the polyhedron. This is obvious by picture, right? Because if I take any x and I take any y, then the set of things that I get when I range lambda from 0 to 1 is I just get the segment between them. And it's clear that geometrically, if x and y are inside this set, then actually if you take any average of them, any convex combination of them, you get something also that's in the set. So a convex set, like this polyhedron P, is one where if you take any 2 endpoints that are contained within it, then the line segment connecting them is also entirely contained within it. So it turns out that this is, a huge dichotomy in algorithm design. For the most part, when you think about where you can actually have efficient algorithms that run in polynomial time, usually the secret sauce underneath it is some representation of the space as a convex set. And a lot of times the things which we can't do are really the natural way, and inevitably you get stuck with non-convex problems. And they have, you know, isolated different pieces where you don't have this property that they're convex. So, you know, the important thing here, just to develop a little bit more intuition, is now what happens when we incorporate something like the objective function c, right? If we're actually trying to maximize this objective function c, what if the direction c points in this direction of the plane, then the optimal solution is actually going to be this point, right? So if we look within this entire polyhedron, which thing maximizes the inner product with c, it would actually be this point. And one of the important things is that for things like LPs, whenever we start off with some feasible solution, some initial guess for what our optimal solution is, and we're trying to optimize it in some direction c, we can actually always make progress by walking around the boundary of it and maintaining the fact that it's feasible, but making the objective function strictly better and better. So that's called the simplex method. It was invented by Danzig, so we're not going to go into details about the simplex method. But it's actually one more example of how we can put a geometric perspective on things that we did. You know, after all, things like, you know, max flow, you started off with a flow, which was some feasible point. So it really was in the polytope of allowable SD flows. But what did we do when we tried to improve it was we looked for an augmenting path. Literally what that augmenting path is it's actually moving along the boundary of some convex body to try and make progress towards sending more total flow between S and T. And the same way when we had things like the min cost flow, and we just looked at all of the flows, the SD flows, which achieve the maximum flow, and we were trying to minimize the cost, we then did was we walked along the boundary using augmenting cycles that would actually strictly reduce the cost. So the same way that we had this principle that we have this kind of greedy algorithm that if the following condition is true, we can make progress, and if this condition isn't true, we're done. That really has some geometric underpinnings that if we can move in a simple way to a neighbor which actually makes progress, we keep doing that until we can't. And when we can't, we really are at the optimal solution. So these are kind of the geometric abstractions. We're going to go into a lot more details about this when we develop algorithms for linear programs. But it's important to keep this type of picture in mind, is that we're developing a geometric abstraction of a lot of the tools that we've already studied. So are there any questions about this? It's a little bit philosophical. I'm kidding. All right. I won't use that trick anymore. All right. Now is weak duality. So let's do more. So we're going to state the following theorem. This is called the projection theorem. I'm going to explain it to you, but this we're actually going to take for granted. It's very simple to prove. We're going to use it to prove something called Farca's lemma. That's actually going to be the starting point of going beyond weak duality to things like strong duality. So this projection theorem actually holds not just for a polyhedron, but if P is any non-empty closed and convex set, then one of the important things is really talking about the notion of projecting into the set. So let me tell you what I mean by this, is that it turns out if you take any point B, in P or outside P, it doesn't matter. Well, I guess the theorem is only non-trivial if it's outside, but what turns out to be true is that there is a unique minimizer to the following function. F of z is z minus b squared over the original set P. So that's the important thing, is that actually if we take any polyhedron, or even in general, any non-empty closed convex set, then we can do is we can take some point outside of it, and we can look for the closest point to it. And it turns out there's always a unique closest point. We're going to call that the projection. And this projection is going to have some important properties. So we'll call the optimal point, let me call it Z star, and we'll call it also the projection of B onto the set P. Okay? So that's claim number 1. Claim number 2 is that Z star is the projection of B if and only if the following condition is met. Z minus Z star transpose times B minus Z star is less than or equal to 0 for all Z in this original polyhedron. So the important thing which is going on geometrically, so let's draw a picture here. So if we talk about some point B, which we want to project, well, finding the closest point, all we're doing is we're actually, I guess let me draw it a little bit down here just to make things simple. So if we talk about the closest point in this polyhedron, then what are we doing is we're taking a circle around B and we're dilating it until it actually hits a boundary someplace. Now, the important thing is that it's going to hit the boundary in a unique place. If it hit the boundary in 2 places, it means that we could have undilated it a little bit and hit it in only 1 place. That's actually how you prove part 1, so I won't really get into this. And if you want to know how to actually prove this, it's pretty elementary. You should think about it, or you can ask me for links. But the important thing is that we have some notion of the projection, which in this case is Z star. And what this lemma is telling us, or this theorem is telling us, is that if we take any other point Z inside the body, and we then take Z minus Z star, so the thing pointing in this direction, and we take its inner product with B minus Z star, then we get something that's non-negative here. And that's important because you can see that here this angle actually has to be off from perpendicular. And we're going to use this to actually prove the simple geometric fact, to prove a lot of powerful things about LP duality. So let me tell you what we're going to use this projection theorem for. This is called Farca's lemma. Are there any questions?
Do you mean non-positive? When you say non-negative?
Do I mean non-positive?
The inner product is it non-positive or non-negative?
Oh, this is non-positive.
Okay.
Yeah. So just this inner product between these two is less than or equal to 0, which you can see from this picture because actually, just to get the arrows right, you've got the vector pointing in this direction, and you're taking its inner product with B minus Z star. So you're actually getting a negative inner product because the angle is more than 90. Yep.
Does that work for any norm, or?
This, you mean replacing the
You need
square
a
with-
strictly convex norm. You mean instead of the Euclidean norm?
Yeah.
So the fact that there's a unique minimizer is a little bit finicky for different norms. So I think for L1, it's not true that there's a unique minimizer. Is that
Also,
correct?
the relation, it's not true, and also the relation to inner products and stuff. Like completely
Yeah, you
goes
need the
away.
dual norm. Exactly. Yeah,
So this,
exactly.
yeah, like this really is a fairly L2 specific argument.
Yes.
It turns out there are some generalizations of L2 squared here, but they're not really other norms.
Yeah. So
There are other functions you can put.
let's take that part offline, but not really. You have to be very careful. For things like 1, even already for L1 norms, there are issues about the uniqueness. For 2, the inner product isn't the right notion because it's not the gradient of the right norm to begin with. This really comes from an optimality condition about from the function you're trying to optimize.
But a concept you might want to look up is the phrase regulating divergence if you're interested in things.
Yes. All right. So let's use this. What I want to do is I want to use this theorem to actually start pulling apart a bit more about the theory of LP duality. So, are you guys all done solving this?
Yeah.
Has anyone been daydreaming and thinking about that instead? No? All right. It's very hard. Let me test that.
I have to stay positive.
Huh?
I had to keep positive.
That's true. Yeah, in fact, I once had a professor who told me, things like this. So this is so simple to state that at some point you have to get worried about things which are that simple to state and still haven't been true. At some point, the hardness of proving it has to cross the line of the truth of the thing to begin with. And that was his phrase for dealing with lots of things like this. But let me tell you about Farca's lemma. So this will be much more interesting now than things like weak duality. So we're now ready to prove what's called Farca's lemma. And there are a lot of different forms of Farca's lemma. I'll tell you about some of the other forms in a minute that actually relates to the fact that you need not take LPs in the canonical form. You could take them in other forms, things like the standard form too. Will all be related to the fact that there are many different versions of the things that I'm telling you. But let me tell you one version, which is going to be directly useful for us. So what I claim is that exactly one of the following holds. Either there is some x which meets the following constraints, ax equals b, and x is non-negative, or there is a y that meets the following conditions. So it's the simplest either-or statement. It's just, exactly one of these two conditions holds. This is sort of the basis for things like strong duality, is that, if you took an optimal solution of the primal and an optimal solution of the dual, the reason they have to meet is because, otherwise you would actually be able to improve one of them. So this is kind of like a baby version on the way to it, which we're actually going to use to prove strong duality next class. But for the time being, all we're saying is that either one of these two conditions holds. So one thing I want to point out is that this doesn't actually look like the canonical form above, right? Because for the canonical form above, we would actually have ax less than or equal to b. And the result is that we get that y also has to be entry-wise non-negative. This is actually another pair, which is called standard form. So this is another duality pair. That's why I'm doing it this way, is because this is called standard form. So the same way, I can change it now. So if we wanted to change things to standard form, we would get ax equals b, and then we'd actually remove this constraint right here. So that's another form of LP duality, and actually the weak duality thing holds the same way for things like standard form. So just as an exercise to yourself, you should think about, now that we've proved weak duality for something like the canonical form, why does actually basically the same proof work for actually proving it for standard form? So I'm going to assume things like that, and a lot of times I don't want to spend too much time thinking about how to go back and forth between them. In a lot of cases, it'll be more convenient to think about the LP one way than the other. The same way that we did things like max flow, it was better to think about it originally in canonical form because it was more natural and easier to interpret. So too, sometimes it's easier to think about things in standard form, and this is the primal dual pair you get. And things like weak duality continue to hold. But now what we're saying is that some version, Farca's lemma is really just saying that in the standard form, if you plugged in something like C is all zeros, then either you're going to have a feasible solution for P or for D, or and that you can't have both. So we're going to prove this lemma And what I'll claim is the following, that what I claim is if both 1 and 2 hold. So there'll be a first part of proving Parker's law, which is relatively straightforward. So what I claim is, when we want to prove exactly one of the following holds, let's imagine both of them hold. And we want to prove a contradiction. Is there a question? No? We want to prove that this can't happen. And what you can do is you can set C equal to 0 in the standard form. And what you end up getting is that Y transpose B, well, that's less than 0. Sorry, is there a question?
Nope.
Nope. All right. So we first want to prove that both 1 and 2 can't hold. So what I'm claiming is that, let's suppose they do. So we take the LPs in standard form. Let's plug in C is equal to 0, right? Because that's when we get out these constraints of things like Y transpose times A is entry-wise non-negative. That exactly corresponds to the constraints in 2. Now, the same way that we proved weak duality for the original canonical form, weak duality also holds for the standard form. What that tells us is that if we had both 1 and 2 holding, then X is feasible for the primal, Y is feasible for the dual in standard form, and yet we have Y transpose B is actually less than or equal to C transpose X, because this guy is 0, and Y transpose B is less than 0, but this violates weak duality. Because weak duality tells us that Y transpose B should always be an upper bound on C transpose X. Yeah?
How do you know the feasible region is not empty? Like if the feasible region is empty in both cases, like
But I'm assuming that 1 and 2 both hold for the purpose of creating a contradiction.
So
I haven't
later
shown
you're going to prove that.
Yeah, yeah. This is one part of it. This is the easy part of the lemma. It's just, we absolutely have to worry about that, because what we want to show is that for these feasible regions, 1 and only 1 holds. The easiest thing to do is to show that they both can't hold, that they contradict each other through things like weak duality. Make sense? Any questions about this? First part of the proof, the rest is to come. Yeah? All right, so now what we really want to prove is we want to prove that not both of these, that at least one of these can hold. So we're going to assume that 1 doesn't hold, and we're going to use it to prove that 2 indeed does hold. So that's a little bit more work, but we're going to make use of this projection theorem. And this is actually the last part that we have to prove today. So let's prove it. Now the bulk of the proof is really, we're going to assume there is no X that satisfies 1. And what we're going to do is we're going to use that we're going to construct a Y that satisfies 2. So let's do that. This is our game plan. So now that we know that both 1 and 2 can't hold simultaneously, what we're going to do is we're going to let P be the set of A times X's that we get when we multiply by something non-negative. Now, I claim that if there is no X that satisfies 1, we can say something about whether or not B is in the set. So what is it? It's not. Right? So by assumption, this assumption, we know that B is not in the set. So now what we're going to do is we know that B is not in the set. We're going to project B into the set. And we're going to use properties about this projection theorem to actually construct the Y and reason about why Y has all of the properties that we need to satisfy condition 2. So that's our game plan, is to how to actually use the separation theorem. So let me build that out. So let's let little p to denote the projection of B into this polyhedron that we've defined right here. So this is little p. And what I claim is that P equals A times X for some X. Just by definition of the fact that this little p really is in the polyhedron. So there has to be some X that realizes it. Yep.
How do we know big P is a polyhedron?
Well, it's convex, and that's good enough.
Enclosed.
And closed.
It's not a polyhedron in general, though. Right?
It's, this one is.
Unbounded.
It's unbounded.
Right. So
Even if it's unbounded, it is. But all you need for this is that it's convex and closed and non-empty. Which is certainly non-empty because I could plug in x's all zeros into it. So in any case, we have the projection onto the set. So now we actually get to the fun part, which is how to actually define y. This is where all the magic is going to happen. And here's how we're going to set y. Y is just going to be p minus b. That's it. And we want to prove that this y works, and then we're home free. So let's prove that this y works. We're going to break it down into two claims. So let me pull this up, and then we'll prove the two pieces of the claim and finish the proof. So once again, I'm going to rely on you guys to help me fill in the details, because now I'll break it down into some claims and give you an idea about how to start off, and then you guys are going to help me. So what I claim is that this y, first of all, meets the following constraints. We definitely need that, because now I've already fixed my y, so there's nothing more I can do but try and show that it really does meet the constraints in 2. So there are two things I have to show. I got to show y transpose times a is non-negative. And then I have to show that y transpose times b is strictly less than 0. So this is claim 1. I'll leave it to your imagination what claim 2 is, but let's do claim 1 first. So what I claim is that, well, we better use the projection theorem somehow. So let's just read off what the projection theorem tells us about our projection. It tells us that for any z in the original polyhedron P, then we take z minus P, the inner product with B minus P is itself non-negative, right? That's just reading off literally what it is. And now all of the magic is going to be, how should I choose the z in here to actually make things work? So this P, I know exactly what P is. This P is A times X, because that's the way that I've defined my X. Let me tell you how I'm going to choose Z here. We're going to choose Z to be A times X plus EI, where EI is the ith standard basis vector. So just the one that has all zeros and 1, 1 in the ith coordinate. Well, let's see what this z tells us, and then we're going to be in great shape. So if we have that z, we're going to get that this entire thing down here is now equal to A times X plus EI. We're going to get an awful lot of cancellations in here. Times B minus P. And now what do we have? At the end of the day, we have EI transpose times A times b minus p is non-negative.
H
Now this
transpose.
guy right here, sorry, is there a question?
Do you mean non-positive?
Sorry,
Do
non-positive.
you need A transpose?
Huh?
EI transpose H transpose.
Yes, my mistake, sorry. A transpose, thank you. Good. So now that we've all agreed that's what I should have gotten, we have EI transpose times A transpose times B minus P. But what is B minus P? That's nothing more than minus Y, right? So what this implies at the end of the day is just the statement that EI transpose times A transpose times Y is non-negative. So now, what's the minor little statement that finishes the claim? Yep.
You need someone for i's.
Yeah, exactly. We set this for all of the different i's, and then we're done. The only way that that could be, if we pull out, all this is doing is it's taking A transpose times Y, pulling out its ith coordinate, that's non-negative. We do this for all of the i's. So we use this freedom that in the projection theorem we can plug in any z we want. We chose a magical choice of z, which lo and behold actually gives us the first constraint. This is the main thing, that this guy is now non-negative. So the remaining claim is actually a little bit even easier to prove. And it's exactly what you think it is. It's just that B transpose times Y really is strictly less than 0. So this is going to be similar, is we're just going to work out what this actually is. So we have B transpose times Y. Let me put it in a more convenient form. So if you remember, so we have this relation between Y, P, and B. So if we pull the B on the other side and push the Y on the other side, we have that B is equal to P minus Y, right? And now we're in good shape, right? Because we know that this part is strictly negative. The thing that we're subtracting off from here, minus Y transpose Y. So it's clear that Y transpose Y is non-negative. Why is Y transpose Y strictly positive? It's the L2 norm. But why couldn't it be the all zero vector?
B is not in.
Exactly. P is not in B, so that means that actually this Y is some non-negative, is some non-zero vector. So we're actually subtracting off something which is strictly less than 0 right here. And all I want to do is prove that this part is itself non-positive. And then I'm done. So let's prove that part. Now what I claim is that all we're going to do is, again, by the projection theorem. So since 0 is in this polytope, then by the projection theorem again, well, we have z minus p transpose times b minus p is less than or equal to 0. This quantity we already agreed on that it's minus y. This quantity right here, when we plug in z equals 0, we just get minus p. So at the end of the day, what we get is we get p transpose y is non-positive. And that's the entire thing, right? So that finishes the proof of claim 2. And now together, if you take a step back and look at what the architecture of this proof is doing, all it's saying is that, when you don't have condition 1 hold, right? And we know that this constraint D doesn't live in the realizable A times X's that we can get. That's a convex set. But what we can do is we can take the B that we would have liked to have been in that set and project it. And that difference in that projection of where it was to where it's going, something like P minus B, that itself ends up giving us a feasible solution of 2. The rest of it was just pulling together the details to show that Y really is feasible for 2. So this is one of the most basic either-or statements. And we get it through the projection theorem, is that either constraint 1 holds, or if constraint 1 doesn't hold, we look at the projection theorem and we use it to construct the 2 that works. So this is the mechanism by which we're going to prove things like strong duality, because we're going to show that if we take two optimal solutions for the primal and the dual, now they actually have to meet. Otherwise, there's actually a way to make progress on one of the two of them. So we're going to be revisiting a lot of these ideas in more detail. So we'll do 2 full lectures on some of the foundations of LPs to get used to how these ideas work. As next time we're going to talk about strong duality. We're going to talk about complementary slackness, and then what I'm going to do is I'm going to revisit this geometric picture and actually talk about how you can think about strong duality as really some sort of optimality conditions that follow from a physics perspective. So the goal is really to build up some intuition for the geometry and to connect to the things we've done so that we can move on to even more interesting things and getting fancy things like approximation algorithms out of LPs and LP duality once we do it. So I'm going to end there. I'll take some more questions offline if you guys have them. But this is the beginning of the LP unit, and we're going to keep working towards unraveling some of these threads.